Okay, let's discuss noise in a communication system. Here is our block diagram for a typical communication system. We start with the message signal x of t, and that's applied to a transmitter that produces a modulated signal, phi of t. Then the modulated signal is transmitted through some medium. Could be connected to an antenna, transmitted through space. Could be a cable, could be any other kind of or a waveguide or some other kind of transmission medium. But in the course of transmission, noise is added. This is we are going to model this as Gaussian white noise, and it is added to the modulated signal, so that the signal that is applied to the receiver is the sum of the modulated signal plus the noise, and then that passes through the receiver, and then we get out the received message y of t. And we need to work with some tools in order to determine the effect of this noise on our output signal y of t, typically in the form of a signal to noise ratio. The model we are going to use for the noise is white Gaussian noise. White light, as we perceive it, has all wavelengths in it. Different wavelengths of light we perceive as different colors. White light has all wavelengths. By analogy, white noise has all frequencies. White noise means it's all frequencies. That's illustrated on this is the power spectral density of the noise. This is an illustration of the power spectral density of the noise in subscript for noise. The double subscript because it's found from the autocorrelation. Although I think we could do with a single N for the subscript, but these notes already have the double. So this describes how the power in the noise signal is distributed across frequencies. So this is frequency across the bottom scale, 0 hertz in the middle, positive frequencies and negative frequencies. The characteristic of white noise is that it has equal power distributed across all frequencies. And that's shown by a constant line for the power spectral density, and the value of this constant is n naught divided by 2. That's the conventional way to illustrate the value of the power spectral density. This would be in watts per hertz or microwatts per hertz or whatever the convenient unit is if we were working a numerical problem. So that's what we mean by white noise. Its power is spread across all frequency, the frequency scale evenly. So it's a straight line when plotted against frequency. We'll look at some other examples of noise. I'll have some audio examples coming up. And there are other colors of noise. This is white noise. There is pink noise. There is red noise. There is what is commonly called brown noise. It's really Brownian. It's another form of a random signal. They all have different spectral characteristics, and we'll see some examples of that in a few seconds. Here's a sample of white noise. I generated this using Audacity, and I've zoomed in close enough so you can see the individual samples in the white noise. This was sampled at 44,100 hertz, so this is CD quality white noise. And it's a random signal, random samples, and I've worked to make it Gaussian so that it has a mean value of 0, and the samples are distributed according to a Gaussian probability density function, or at least an approximation of that, so that it's more probable that the values are small and lie close to 0, but every occasionally we have values that are higher, larger, either positive or negative, and lie further away from 0. And this is what the noise sample sounds like. We can look at the spectrum here. Let's see, plot spectrum, and this is an approximation of the spectrum of this noise sample, and you can see that it is constant, relatively constant over the range of frequencies that can be represented with our particular sampling rate. And that's the characteristic of white noise. It has equal power over all frequency intervals. To show the contrast, this is a sample of pink noise, and it looks different. Doesn't look as widely distributed, but what the difference is more apparent in its spectrum. Here, first, let's listen to what the noise sample sounds like. It is much lower in pitch. Let's look at all the, let me look at the spectrum. And this is the spectrum, the approximate spectrum for this pink noise. It's a bit difficult to see on this. This is a linear scale for the frequency, but you can tell the lower frequencies have much more power content, or much more power content than the higher frequencies. I think if we show this on a log scale for frequency, you can see that the intensity of the noise drops off. It's on a straight line on the log scale, but low frequencies are more represented than high frequencies. Again, for comparison, this is often called brown noise. It's Brownian, I think, is a more proper term, but let's listen to it and see how it compares. Now let's look at the spectrum, and it appears to drop off even more quickly for the higher frequencies. If we put this on a log scale, it has a different spectral line compared to the pink noise, and it again represents has more content at lower frequencies than the higher frequencies. So the noise model we're going to use is Gaussian white noise. So it has equal power distributed over all frequencies. Let's consider what happens when we take this Gaussian white noise represented by this power spectral density, capital S with the subscript N for noise. It's a function of frequency, and we pass it through a linear system that's described with transfer function capital H of F. Now, what will come out will be band limited noise. So this is band limited noise. It's the noise that has been passed through this low-pass filter in this case. And what we've worked out when we were talking about random signals is the power spectral density of the output of this linear system will be the power spectral density of the input, which is a quite simple function, simply a constant n naught over 2, multiplied by the transfer function squared of the linear system. So if we use an ideal low-pass filter, that would make the transfer function equal to, let's give it a gain of 1. It's described by a rectangle of f divided by 2 times the bandwidth. So if we plotted this transfer function, it'd be quite simple. It's a rectangle with a gain of 1, and it goes from minus b to plus b, so the overall width of the rectangle is 2 times b. So we describe this as rect of f over 2b. And then when we take the transfer function squared, magnitude squared, as we need to do to find this power spectral density, well, the magnitude squared of well, let me put it this, the magnitude squared of this transfer function for this rectangle, it's either 0, 1, or 0. So it's the in this case, it simply equals the magnitude of the transfer function itself. This is only good for rectangles, good for the rect function. If we had some other shape for this transfer function, this obviously wouldn't be the same. Our mileage would vary, and we would have to do something else. But so we can now write the equation for the power spectral density of the band limited noise as a function of f is going to be the power spectral density of the input signal, which is, we saw here, simply n naught over 2, n naught over 2. And then we multiply by the magnitude squared of this linear system transfer function, which is simply going to be rect of f divided by 2b. Okay, so that's quite simple to write. And now that we've got the power spectral density, if we wanted to know the autocorrelation of this random signal, see, that's going to be the inverse Fourier transform of the power spectral density. And so that's going to be, this is the autocorrelation of the band limited noise as a function of tau. So this should not be f, this should be a function of tau. Inverse Fourier transform, n naught over 2, is simply a scale factor. Then we take the inverse transform of this rectangle, and we get 2b times the sinc of 2b times tau. And so the autocorrelation is going to be, the 2's cancel, it's got to be n naught times b times the sinc, and we can write this as tau divided by 1 over 2b. And this would be the now the autocorrelation for the band limited noise. And this is what that looks like if we plot this out. Again, I've got a double n subscript. We could do it with the well, this is band limited noise as a function of tau is n naught times b. That's the value here at its highest point. And then that multiplies the sinc shape, sinc of tau divided by 1 over 2b. So it's a function. This should not be an f. This should be a function of tau. And it should have its first zero crossing at 1 over 2b. And then the next zero crossing is at 2 over 2b. And then 3, 4, 5, 6, etc. And it goes in both directions. It's symmetrical with respect to tau. Okay, so this is again the autocorrelation. Let's find the total power in the noise that is passed through this low-pass filter. We've written the power spectral density of the band-limited noise with this equation. So let me sketch that. This is frequency. This is the power spectral density of the band-limited noise. It is a constant multiplied by this rectangle that goes from F is equal from minus B to plus B, so it gives it a bandwidth of B, and it has, the rectangle has a height of N0 over 2. The noise power, let's call it N for noise power, total noise power is going to be the integral from minus infinity to plus infinity of the power spectral density, and we're integrating over all frequency. So we have to evaluate this integral. In this case, it's very simple because this integral is simply the area underneath this rectangular shape, and even I know that the area under this rectangular shape is going to be N0 over 2 is the height of the rectangle, and the overall width of the rectangle is 2 times B, and the 2's cancel. So the noise power N is equal to this constant N0 times B. So this is the noise power of the band limited noise in watts. It's so it's the average power, you could say, as well. It is dependent upon two things: the intensity of the background noise, as indicated by the value of N0. It is also directly proportional to the bandwidth of the low-pass filter. See this value of B? That's the bandwidth of the low-pass filter. So this is the bandwidth of the low-pass filter. So the wider the bandwidth of the low-pass filter, the more noise power is allowed through the filter. Just to back up the idea that this is a reasonable model for noise, I'd like to look briefly at what is called thermal noise. If you pass a current through a resistor, even if you intended to pass a constant current through the resistor, if you were to measure the voltage across the resistor, you would not see, on an oscilloscope, you would not see simply a straight line in time. You would see fuzz on the line. It would be a fuzzy line. Now, there's a good question: is that noise coming from the voltage fluctuations across the resistor, or is that noise coming from some kind of noise source inside the oscilloscope itself? That's a good question to answer. But either way, there will be the line on the oscilloscope will not be perfectly straight. There will be some fluctuations caused by noise, and that noise in some cases is caused by thermal noise in the resistor. So you attempt to pass a current through a resistor, but due to the temperature of the electrons and the atoms in the resistor, there are electrons vibrating in all sorts of random directions. Sometimes they vibrate in the same direction as the current flow, sometimes they vibrate in the opposite direction of the current flow, but the result is that the current flowing through the resistor is not a constant. It fluctuates randomly. Now, if the amount of the fluctuation is relatively small, no doubt, but if you were to thankfully, it's beyond the scope of this course, but the power spectral density of the thermal noise in resistors has been worked out, and it follows this kind of equation for the power spectral density. It involves the value of the resistor, it involves H is Planck's constant, F is frequency, and this is just the absolute value of the frequency, and then it's an exponential function, again Planck's constant, the frequency. K is Boltzmann's constant, T is the temperature of the resistor in Kelvin, One is a constant, and if you plot this as a function of frequency, this is the kind of shape you get. But you'll notice that this power spectral density is very constant over a very wide range of frequencies. 0 hertz, kilohertz, megahertz, gigahertz, kilohertz, kilohertz, megahertz, gigahertz. So up until what is that, like 7 or 8, who knows, gigahertz, it's still showing relatively constant. Well, this range of frequencies is pretty much the range of frequencies you could build electronic circuits for. If you get up to the higher end, you're moving into microwaves, and that's a different kettle of fish. So for the frequencies over which electronic circuits are being built, the thermal noise in a resistor is constant, relatively constant. So it seems like a reasonable concept to model the noise in these systems as white noise. It is approximately white over the frequency ranges that we are interested in. Now let's pass the Gaussian white noise through a bandpass filter, and the bandpass filter will have a transfer function that looks like this. It will be centered at frequency f0, and the bandpass filter has a bandwidth b, so it can be represented by a pair of rectangles, and the power spectral density of the noise that comes out of the bandpass filter, this is what is illustrated here, is simply this pair of rectangles as a shape, and the height of the rectangles is given by n0 over 2. So this is the power spectral density for the Gaussian white noise that has been passed through this ideal bandpass filter. And we can write the equation quite simply. It's written in this form. We have this is the shape of a rectangle with height n0 over 2 times a rect f over b. So this is a rectangle with width b, and now we're convolving that with a pair of delta functions. These are delta functions on the frequency scale. So we're replicating this rectangle shape at plus f0 and also at minus f0. And then the total power is shown here with the variable p. I need to keep my variable straight, I suppose. I used an n on the previous page, but here the average power is p, and it's going to be the total area underneath these two rectangle shapes. See, the power is the integral from minus infinity to plus infinity of the power spectral density of the noise with respect to f, and so it's simply the total area. Each of these is n0 over 2 times b. When you add the two together, you get a total power of n0 over b. And again, the average power that makes it through the filter is proportional to the bandwidth of the filter, and we get exactly the same result as we did, or the same equation for the result as we did with the low-pass filter. Now to find the autocorrelation of the noise as a function of tau, that's going to be the inverse Fourier transform of the power spectral density. So the inverse Fourier transform of this equation, n0 over 2, is simply a amplitude scale factor. Inverse Fourier transform of the rectangle is going to be b times the sinc of b times tau. And then this convolution will be now a multiplication. Inverse Fourier transform of this pair of delta functions is 2 times the cosine of 2 pi f0 times tau. And so the 2's cancel, and we get as the autocorrelation n0 b times the sinc, and this is tau divided by 1 over b, and then that multiplies cosine 2 pi f0 times tau. So if we were to plot that, this is the kind of shape we get. Here this is the same equation that I just wrote out. We've got in the modulating the amplitude of this cosine, that's a function of tau, as this sinc function, and at tau equals 0, the sinc has a value of n naught b, so that gives us the maximum value. The 0 line runs right through the middle of this, so it's n naught b at the top and n naught b minus n naught b at the bottom. Then the sinc function has 0 crossings at 1 over b and 2 over b and 3 over b. So this is penciling in the sinc function, which forms the envelope for this cosine that has a frequency of f naught, which is the center frequency of the bandpass filter. So to draw the function, you mirror image the envelope, and then this cosine falls inside that envelope. So this now is the autocorrelation for the noise after it's been passed through a bandpass filter. Something interesting happens when we pass white noise through a bandpass filter, especially a bandpass filter that is relatively narrow in bandwidth compared to the center frequency. And we're going to work out a model for this narrow band noise. This is narrow band noise. It's been passed through a narrow band pass filter. Okay, so the noise signal itself, here's a numerical simulation of the random noise. I generated this using MATLAB again, and the dots are connected so you can see how the noise changes randomly. I had MATLAB do an autocorrelation to estimate the autocorrelation for this random noise, and this is what we get for the autocorrelation. It's got what closely resembles a delta function, has a height of 1 right here at tau equals 0. So with no time shift at all, it is 100% correlated with itself, as you would expect. But even with the slightest of time shifts, again, there are limitations due to the sampling, and so even if you shift it one sample to the right or to the left, the correlation drops to 0. So this is a pretty close approximation of a delta function. And this then is the autocorrelation for this Gaussian white noise. Now, if you take the Fourier transform of the autocorrelation, you get the power spectral density. This is the power spectral density of the Gaussian white noise found by taking the Fourier transform of the autocorrelation, and you can see that it is for all practical purposes a constant straight line. It's because I'm using random sample functions, we still have some randomness in it, but if I took enough examples and averaged them out, this would get smoother and smoother. So this is the power spectral density, which is essentially a constant. I took this Gaussian white noise that generated with MATLAB, and I passed it through a bandpass filter, again generated by MATLAB, and this so we had the white noise pass through a bandpass filter with a certain center frequency. I chose 200 Hertz just because it made a presentable picture, and the bandwidth chose as 40 Hertz, again just because it made a presentable picture. These are not really illustrative or good examples numerically of what one would do in practice in a communication system, but the picture turns out nice. So then I looked at the noise that, or the signal that made it through the filter, and plotted it out, and this is the result that this is what resulted. This is white Gaussian white noise passed through a narrow bandpass filter. Actually, it's not all that narrow, but still, it's an approximation. And I picked the values to make the picture nice, and you can see something interesting. You see that it looks pretty much like a sinusoidal, a sine wave, a sinusoid, and it is obviously changing in amplitude. Its amplitude is relatively slowly changing. So, and it turns out that the frequency is 1 over, or the period, I should say, is 1 over the center frequency of this bandpass filter. So frequency is 200 hertz. So 1 over 200, I'm using my calculator to find that that's 0.005. So you can tell that the period between these peaks is about 0.005 seconds. So then the amplitude changes, and it changes. I think that would be related to the bandwidth. I didn't run more experiments to see how that would look, but nonetheless, we've got a slowly changing amplitude. And it's not visible to the naked eye, but the phase the instantaneous phase would also be changing. Now that's not really visible, but I'm going to assert that we have also a slowly changing phase angle, and but we can model this as a sinusoid at the frequency, the center frequency of the bandpass filter, and it's a random sinusoid with a slowly changing random amplitude and a slowly changing random phase, and this is what the noise that makes it through the bandpass filter looks like. Say the narrowband noise appears to be a sinusoid with a slowly varying amplitude and phase. The nominal frequency, this nominal frequency is the same as the center frequency of the bandpass filter. If we take this noise signal and do an autocorrelation, this is the shape I get. This envelope looks like it might be some kind of sync squared shape. It's not really a triangle. It looks kind of triangular though, but this was numerically found by taking the Fourier transform of this random signal, and it gives us this autocorrelation. Now, the power spectral density of this narrowband noise is found by taking the Fourier transform of this autocorrelation. So I had MATLAB do that, and this is the result of the Fourier transform. And this is the power spectral density, and you can clearly see that first of all, it looks like a pair of narrowband shapes. It's centered at plus and minus 200 hertz, and it's got a bandwidth that is I'm going to say that's about 40 hertz, as we had in our bandpass filter, and it looks a little bit like a delta function, but it's wider than a delta function. It's not quite rectangular in shape. It's got a curve to it. But this now is the power spectral density of the noise that has been passed through a bandpass filter. Not an ideal bandpass filter, which would be a pair of rectangles, but a more practical bandpass filter that is being simulated in MATLAB. I don't remember the characteristics in terms of what order of filter it was. I'm sure it was a Butterworth filter of a particular order, and I don't remember. Maybe somewhere deep in my notes I could find that value, but that would take an afternoon. But nonetheless, this is the power spectral density of narrowband noise. So to represent this narrowband noise that looks like a sinusoid with a random amplitude and phase angle, this is the narrowband noise represented as the real part of a phasor representation. So we take e to the j 2 pi f naught t, that would represent the sinusoid, and for its amplitude, let's have a random signal for its amplitude, N for noise, and we'll break this amplitude into two components, an in-phase component and a quadrature phase component. NC is that is the in-phase component. If you looked at it as a phasor, that would be the component of the noise that's pointing in the direction of the real axis. It could be positive. It could also be negative. It would vary randomly as a function of time. Then there is a quadrature phase component, N with a subscript S. That's in line with the imaginary axis. I've shown it pointing upward here, so it has a positive value. This also varies randomly in size, and the total noise is given by the resultant phasor A as a function of time, which is going to be the in-phase phasor added to the quadrature phasor. And so this now is the random vector. It has a random amplitude, A of t, and it also has a random angle, theta, with a subscript n. So this is the random angle. Okay, but we're representing it here as the real part plus j times the imaginary part. So the in-phase component plus j times the quadrature phase component. And multiplying that as the amplitude of this exponential to represent the cosine, then we take the real part, and this will give us our representation for the noise. So this e to the j 2 pi f naught t is cosine 2 pi f naught t plus j sine 2 pi f naught t. And then when you multiply these across each other, we get nc of t times a cosine plus nc of t plus j times a sine, and then j ns of t times a cosine plus j times j gives a -1, ns of t times the sine. So here all four terms are printed out. We're taking the real part, so the two imaginary terms we can scratch out, and we're left with nc of t times cosine 2 pi f naught t minus ns of t times sine of 2 pi f naught t. And this is the model for the narrowband noise. In C, the in-phase component, and in S, the quadrature phase component, are slowly, relatively low-frequency random noise processes. So NC is a value that's changing randomly, both positive and negative, relatively slowly compared to the center frequency of the bandpass filter. And NS is also a random component changing relatively slowly compared to the center frequency. The fact that it came out as a minus is of no real concern to us, really, because it's random, both positive and negative. Okay, so this is the model for narrowband noise, and we can use it. It's useful in this form when we look at passing the noise through the asynchronous demodulator, such as we would use with double sideband or some other demodulation process. So the narrowband noise can be represented using this phasor representation as the in-phase component NC times cosine 2 pi f naught t minus the quadrature phase component NS of t times sine of 2 pi f naught t. With a little trigonometry, the cosine and sine can be joined together as a single sinusoid with a random amplitude A of t times cosine 2 pi f naught t plus a random phase angle phi of t. And so A of t would be the square root of NC squared plus NS squared. and the angle, the random angle, is the inverse tangent of the imaginary part divided by the real part. So this is essentially turning this this from a rectangular form into a polar form. It turns out, and won't go into this in any detail, but it turns out that this amplitude, the random amplitude function, is described by what is called a Rayleigh probability density function, which is plotted out here. It has zero probability of being negative. It only has positive values for an amplitude. That makes sense. And it takes this kind of shape, which is described by this equation. A is the value of the amplitude. Sigma A squared is the power in the narrowband signal noise, and we can calculate that, so we can use that in this equation. And then it forms this kind of shape. This is for sigma A squared equal to 1, and it turns out to have a maximum value at A equals 1. And that's where the most likely value is in this range. It could go all the way down to 0 with vanishing small probability, and it could be somewhat larger than 1, and the probability drops off in that direction as well. But this gives the probability of the value of the amplitude, and it is a random signal. The phase angle is also random, and that is important too. And the phase angle has a uniform distribution. So this is the probability density function for the angle phi. It is a constant between 0 and 2 pi. It's shown here in radians, and since its width is 0 to 2 pi to make its total area 1, it has a value of 1 over 2 pi for this entire range of frequencies. Okay, so this describes now the random phase angle for the noise. So to use these noise models in analyzing the performance of various communication systems, we will apply them to this kind of model, where we have the message signal applied to a transmitter producing a modulated signal that is passed through a transmission medium, and added to the signal, to the modulated signal, is additive noise. So this signal plus noise is applied to the receiver. Now, at the input of the receiver, we have a certain signal power in and a certain noise power in, and we can determine the quality of the signal going into the receiver by its signal to noise ratio. And coming out of the receiver is a signal shown here as y of t. And in an ideal world, I suppose, you would have y of t as an exact replica of x of t. But it's not necessarily so. But it is certainly we can extract the information we desire out of this signal successfully, one hopes. And this output signal will also have a signal power out and a noise power out, and we can determine the quality of this signal by its signal to noise ratio. And then we can compare the signal to noise ratio in to the receiver to the signal to noise ratio out of the receiver, and determine which form of receiver performs better with respect to noise. So we can now compare one form of modulation to another form of modulation in terms of its noise performance. So the noise, the additive noise, is zero mean, has an average value of 0, Gaussian distributed. So the probability of the instantaneous value has this Gaussian distribution. White noise, so it is constant over all frequency. And the power spectral density is simply this constant n naught over 2. The noise is, I left out an O, I didn't spell the word noise here. This is a noise, is uncorrelated with the modulated signal. So the noise is not related in some way to the modulated signal. the noise is additive. There are other forms of noise that are related to signal that would be signal dependent noise, which are very difficult to correct, or at least even to analyze sometimes. But uncorrelated additive noise is what we are dealing with. If we look at the total power into the receiver, so the modulated signal plus the noise, that would be phi of t plus n of t. We want to find the total power, so we square this signal, then take the time average. When you do the square, you get a phi squared term, then you get a cross term, 2 times phi times n, then you get an n squared term, and then for the time average, we can time average each one individually. The term in the middle, the cross term, is going to time average to 0 because two things. The modulated signal is going to have a 0 average, and the noise is going to have a 0 average. So you multiply the two together and you get a function with a 0 average, and a function with an average of 0 averages to 0. So now we have the modulated signal average power plus the noise power. So the total power is equal to the signal power plus the noise power. And in these circumstances, we can measure the quality of the signal by the signal to noise ratio. We take the signal power divided by the noise power, and that will give us the signal to noise ratio. This is a power ratio, has no units. And the larger the number, the better. Big signal to noise ratios have big signals and small powers. Big signal and small noise. So that would be a high quality signal, or at least a higher quality signal. So we want that to be big to improve the quality of the signal. And the signal to noise ratio is often expressed in decibels. So you take the signal to noise power ratio, take the log base 10, that would be in bells, multiply by 10, and that would be then in decibels, lowercase d, uppercase b for the abbreviation. And these are now the noise tools we will apply to the various communication systems.